If you really want to get a handle on linear algebra, you've got to start at the very beginning. And that beginning, the absolute root of it all, is the vector. It's the key that unlocks, well, everything else. So here's our game plan. First, we're going to tackle the big question. What even is a vector? Then we'll look at it from 3 totally different angles. We'll nail down how linear algebra specifically thinks about them, cover the 2 most important things you can do with them, and then finally, we'll see why any of this actually matters.
All right, let's just jump right in. What is this thing, this one concept that an entire field of math is built on top of?
So when we use the word vector, what are we really talking about? Well, it turns out there's not just one simple answer. You can think of it in 3 different but really closely related ways, and getting all 3 is the real key to understanding them.
We're going to check out these 3 different viewpoints, one from the world of physics, one from computer science, and one from pure mathematics. Each one gives us a really unique and, honestly, a super useful way to think about vectors.
So yeah, to really get what vectors are all about, we're going to look through 3 different lenses. We've got the physics point of view, the computer science point of view, and then the more abstract way that mathematicians see it. Let's break them down.
For a physicist, a vector is basically just an arrow floating in space. That's it. It's all about 2 things, its length and the direction it's pointing. You can literally pick that arrow up and move it anywhere else, and as long as its length and direction don't change, it is the exact same vector.
Now, for a computer scientist, vector is just a kind of fancy word for a list of numbers. The key thing here is that the order of the numbers matters. So, for example, you could describe a house with a 2-dimensional vector. The first number could be its square footage, and the second number could be its price. It's just a way to package related data together. And then you've got the mathematician's perspective, which gets beautifully abstract. To a mathematician, a vector can be pretty much anything at all, as long as it follows 2 simple rules. You have to be able to add 2 of them together, and you have to be able to multiply one by a number. This view kind of wraps up the other 2 by focusing only on the operations you can perform. So, how does linear algebra take these ideas and make them its own? Well, it's pretty clever. It basically merges the arrow idea with the list of numbers idea by giving every vector a specific starting point. And this is the crucial difference. Unlike in physics, where vectors can just float around, in linear algebra, their tail is almost always anchored right at the origin, the 0, 0 point at the center of your graph. It seems like a small tweak, but it has some massive implications. Once a vector is anchored at the origin, its coordinates are just a simple set of instructions. For a 2D vector, the first number tells you how far to walk along the horizontal x-axis, and the second tells you how far to then walk up or down parallel to the vertical y-axis. It's just a recipe for getting from the vector's tail to its tip. And hey, just a quick note on how we write these. The standard way is to list the coordinates vertically, as a column of numbers inside square brackets. It's a handy way to make sure we don't confuse a vector with just, a point on a graph. Okay, now we are getting to the absolute heart of it all. Pretty much every topic in linear algebra, no matter how complex it seems, boils down to 2 fundamental operations, adding vectors and multiplying them by numbers, which we call scaling. So how do we add 2 vectors? Well, geometrically, you use what's called the tip-to-tail method. You just slide the second vector over so that its tail starts at the tip of the first one. The result, their sum, is the brand new vector that goes from the original tail to that final tip. And numerically, it's even easier. You just add the matching numbers from each list. First number plus first number, second number plus second number, and so on. Simple. There's a really great way to think about this. You can imagine each vector as a certain movement, like taking a step. So if you take one step along the path of the first vector, and then you take a second step along the path of the second vector, where you end up is the exact same place you would have gotten to if you had just taken one single step along their sum. The other fundamental operation is scaling. This is just what happens when you multiply a vector by a regular old number. We call that number a scalar, and its only job is to stretch, squish, or sometimes even reverse the direction of the vector.
Let's make this real. If we take a vector and multiply it by the scalar 2, we're just stretching it out so it becomes twice as long. But it keeps pointing in the exact same direction.
But what if we use a negative number, like negative 1.8? Well, that does 2 things. The negative sign flips the vector around 180 degrees, so it points in the complete opposite direction.
Then, the 1.8 stretches that new reversed vector to be 1.8 times its original length.
And if you're thinking about the numbers, this is just as easy as addition. To scale a vector, you just multiply every single number in its list, every component, by that scalar. That's it.
So, okay, we've got vectors as arrows and vectors as lists of numbers. But the real magic, the true power of linear algebra, comes from being able to translate back and forth between these two ways of thinking.
This translation ability is like a superpower across so many different fields. I mean, a data analyst can take a huge spreadsheet of numbers and visualize them as vectors, making hidden patterns suddenly pop out. A physicist can describe the geometry of physical space with numbers that a computer can actually work with. And someone in computer graphics? They represent 3D objects as lists of numbers, so they can calculate exactly which pixels on your screen need to light up.
And that kind of leaves us with a final thought to chew on. The core idea we've seen today is about translation, about shifting your perspective. It's incredibly powerful to be able to move between the worlds of geometry and numbers. So it makes you wonder, what other ideas could we understand in a completely new light if we just found the right way to translate them?